Okay. So this is start this class. So we shall first start by writing down the covariant derivative of a contravariant vector AA. And that we know that we have already obtained the formula for this. Right. This A is what it is, and this we shall call it this A. Because there are two free indices, so this is something like this. We shall now calculate this. And if we calculate this, take another covariant derivative. So this is basically nothing but some of our notation that we have used. This is just for convenience. Then we use this notation TAB, and this will be therefore C. Now for the contravariant index, write it is A, C, D, D, D. And for the covariant index, we write it in this way. Gamma will be in there, C, C, B, A. Please check whether you understand this or not. Okay. You should, by now, you should be comfortable with writing covariant derivatives of any mixed tensor. And this now, what we shall do is, we shall put over here, LC, D, AB is del B plus A, BC. So that gets this changed to D, BE. This term. So we have replaced C here. C was the wrong index. We have replaced it by D because there is already a C sitting over there. Okay. So there cannot be three C indices. So it will change that. Now this is gamma A, CD, EDB. EDB is nothing but del G D plus gamma D D E. Please check whether we read correctly or not. ABC, BD, BD is there. And then minus gamma AB, that is del B A plus A B. Okay. डेल डी होगा हाँ उनका लास्ट का आता है डेल डी ए ए डेल डी का डेल डी ठीक है क्या ठीक है बोलो डेल डी वेरी गुड थैंक यू डेल डी ए so now what we shall do is we shall just multiply these out. So if you multiply these, that is equal to del C del B is A plus del C gamma A B. So we have two terms. This multiplied by AB plus gamma A BB del C AD. We have two terms from here because we will add from two terms. Then we will just multiply these things. This will be gamma A CD del B. AD, this one. And then we have another term which is gamma A CD gamma E. Then these two terms is minus gamma E CD del B A minus gamma E CD A. Please check all your indices whether they are correct. I have made any mistake, I can make mistakes. Please check whether you should have three free indices. That is the check. So check all the terms whether there are three free indices and all repeated indices appear twice, not more than twice. So we have this, and now what we shall do is we shall calculate another term. So this is basically grad C grad B A. Okay. And now what we need to do is we just move this part. We shall calculate another term. Shall now calculate grad B grad C. Okay. So if you do that, you should be able to write it down yourselves. So please write it down. So we are just writing BC. So in this we have to just replace, right? Very good. Replace C by B and B by C. Then C, comma A C B B plus gamma A C B then B plus B B is B B minus. Please check whether I have done it correctly. Then gamma B C B C this is A minus gamma B once again BC Is that correct? Good. And now what we shall do is subtract this from this. So if you do a subtraction, then what shall we get? There will be another term. How many terms are there at 1, 2, 3, 4, 5, 6, 7? 1, 2, 4, 5, 6. I missed one term, right?
Gamma A, BD, gamma D, CD.
Which term did I miss?
The minus are
This one.
third. That's the third.
Which term? I missed that term, right?
Yes.
Gamma A, BD, and then C, AD. Let me just write this term. I missed this term, right? Very good. So gamma A, B, D, gamma D, C, okay. So let us subtract this from this. So if you subtract, then you can immediately see that this cancels with this term. One. And here to find other terms which cancels each other.
Second last term.
Second last term. This one. This one is which one? Gamma D,
Previous and last
C,
term.
gamma A, A, E. So this one will cancel because of the fact that the affine connection we are using is symmetry. Okay, so this will cancel.
Previous term.
There will be AA, so this one will also cancel. This one also goes away. So we have any other term that will cancel? No more terms, right? Let me just check.
The last.
The derivative del CAD, the derivative goes
Del C,
del CAD. Okay, উপরে 3 নম্বরটা আমার এটা
or
4 নম্বরটা উপরে 3 নম্বরটা
gamma A, BD, del C, AD. So this will also cancel. Good. This also goes away.
Parameter.
Any other term?
The previous term.
This one?
No, second last term. First line, last term.
So the next one, this one. Gamma A, C, D. So where is that term? There will be AD. So this cancels with this one, right? So you can see how many terms are surviving. One. This is the term that survives. 2, 3, 4. There are 4 terms which survive. Okay. So let us write it down. I don't know where should we write it down. Have some space here. So write it down here. So grad B, grad C minus so if we write this down, this is equal to the first term is del B comma A C A D. So this minus this, we shall have minus del C comma A B D. So these are the 2 terms that we have taken care of, and then we have this term plus gamma A E gamma E. C, AB, this and this. Minus gamma A, C, gamma B. So that is all. Please check whether you have got this or not. You have got it? Good. Manjuri, you have written down this part? So what we have done, you came a bit late, what we have done is, we have first calculated gravity AA, then we have calculated this term, and once you calculate this term, you just replace, this is B and C, then you will get the other term, and then we have subtracted this term from this term. That is what we have done. So let me just write the result now. So that particular combination, we can write it down as grad V, grad C commutator, combination that we have written there. That is equal to, I think I have used index A. What we can do is, we can write this form there B A B minus del C A B. মাঝখান দিয়ে সেটাই করবে প্রথম দুটো করতে পারো তুমি হ্যাঁ একই ব্যাপার যেটা তোমাদের কনভিনিয়েন্ট হয় সেটা করো আমি আমি যেভাবে করেছি আমি সেভাবে তুমি তোমার মতো করতে পারো একই ব্যাপার not a problem what should be saying is that you can change here key and then take on it's fine it's not a problem but whatever you do should be consistently done take care of indices so I shall and what I am doing is I am replacing this by E and by B. I'm just waiting because I did it in my notes. It is I've done it like that. I don't want to deviate much from my calculation. So later on, I have to just match my indices. So gamma A B E gamma C B minus gamma A C B. You can use your indices and take AE out. Just replace E by D and take AE out. Good. So this is what we have. And this thing, so write it down as R A B E B J B. Okay. Another reason for writing it in this way, because if you had done it that way, then you would have got an E over here. A B C E. So that sounds a little bit odd, maybe. That is why it is good to keep A B C D. So what we have done is we have called this term inside the bracket to be some quantity, which is this. Okay, and this term in the bracket is actually, so what is important is that this is a covariant derivative. This is what? This is a vector of, this is a tensor of rank 1, this is a vector contravariant vector. So this thing transforms covariantly. Right hand side must transform covariantly. AB transforms covariantly. So this thing must transform covariantly. Therefore, this thing is a tensor. The first thing. So the object inside the bracket, even though it may look that gamma is not a tensor, it does not transform in a covariant way, but this combination must transform in a covariant. The first thing. And this object is called the Riemann curvature tensor. Because it gives us a measure of how much the space is curved. Why? Because if you think physically what has happened, we have computed this object and we have got this result. From this result, we have identified a tensorial object, which is this, which is a combination of gammas. But why is this why is this object measuring the curvature of space? The answer is quite simple. The answer is the following. See, what is the covariant derivative doing? What is the job of the covariant derivative? The job of the covariant derivative is to take you from one point to another point. You are basically transporting it, and basically it is a way by which you can differentiate two vectors. Right? You are parallel transporting from one point to another point. Parallel transporting a vector. So this grad V A means what? You have parallel transported this vector by this to some point. And then the resultant object that you got, which I have called TAB during my calculation, you are transporting that object by this covariant derivative to another point. And the reverse is just the opposite way. You are transporting first this object to some different point by this covariant derivative, and then you are transporting to this. Now the question is whether the final result that you get is same or not. And what you find is that the final result, so what you are doing is you are going from this point to this point, then you are going from this point to this point, then you are going to this point to this point. The question is whether the final result that you get is the same or not. What do you think? Is the final result the same? Final result is not the same. If the space in which you are working has a curvature, then the final result is commutator of the two covariant derivatives. They do not commute. Is equal to something this. If the curvature is 0, then these two covariant derivatives will commute. Then only if the space is flat, then only the two covariant derivatives will commute. Otherwise, it will not commute. And it will not commute by what factor? It will not commute by the factor which is given by this, which is a measure of the curvature of the space in which you are working. So this Riemann tensor is actually measuring the curvature of space. If the space has no curvature, then this will be 0. Then the two covariant derivatives will commute. So this is the physical meaning of whatever we have done so far. So if you have any questions, you can ask at this point. Do you have any questions? So, any calculational point, anyone who has not understood? If this is fine, then we shall now, the rest of the lecture, we shall concentrate on this Riemann curvature tensor. So, we have understood what this Riemann curvature tensor is. This is RA, B, B. And there is a nice way of writing this. If you note the formula of Riemann curvature tensor, you will find that there are two derivatives of Christopher's symbol, affine connection, which is symmetric obviously. there are two derivatives of the affine connection. So it is, the structure is something like this. Two terms which are derivatives of the Christopher connection, and two terms which are products of the Christopher connection. Just remember this structure. That is all. Riemann curvature tensor you don't need to memorize, but you can write it immediately. Is del gamma minus del gamma plus gamma minus gamma. Now you have to just put in the indices. Indices putting is very easy. You start with this, del C. If you start with this, so this is C, put it in the derivative. A must sit on top, right? So you put all A's on top. Huh? Oh, sorry, the answer is cannot be here. Very good. Thank you. So don't need to put there, just put one A. And now what we can do is C is here, A is there, and the remaining two indices are B. So this is done. You can put it in any order. You can try also B, whatever it is, because we are using symmetry of connection. So this is done. And now the next term you put B over here. Just concentrate on these two indices. So if you put B over here, what remains is BC.
It will be
Just a
B.
minute. This unit. Del B BC. This is fine. What is the problem with this? Let me just check. I think this is correct.
Last two terms are
Excellent. Del C gamma A. That's del B gamma A BC. What is the problem?
This will be del B gamma A CD minus
Del B.
del B gamma A CD minus del
Yes,
C
yes.
gamma A BC. So we write.
That's what we derived.
Yes, sir.
Just a minute. Grad B, grad C, A. Okay. Oh, that's what we derived. I don't know why we get this thing. Gamma A. Just a minute. No. There must be something problematic there. There must be something problematic. Okay. Anyway, there is a problem. The thing that I wrote down, it is actually a matter of convention, but just a minute. Just tell me the result that you derived. The result is there, right? That is the result. But you have to be a little bit careful with that. So that is grad B, grad C. It's actually a matter of convention, but you should be careful. Grad C, grad B, AB, AA. This is basically grad B, C. Correct. Grad C, grad. This is correct. And that is the result that you have got. Now this one needs to write it as R A B C. Please change it to this thing. This is a matter of convention. Why this is used, I am not sure, but this is how you write it. You could have written it BCD, the way I have written it down, but you have to write it as RADBC. Now everything will be fine. If you do it in that way, then you have to again do one thing. This is the following. This is RADBC. It has been done not only for convenience, all the formulas will come out in a very nice way. You could have actually done it, done it in the way in which I did it, RA, BCD. But then you have to do all your own convention and set it up here on your own. Because what we shall study is, we shall study the symmetries of this curvature tensor, but it is a convention, it is usually written because there is, I can actually call this to be some R, A, B, C, D. So R is doing this. Because D is being summed over, you can put the object like this, but then you have to work out all the symmetries on your own. That is why it has been put it in this. So once it has been done in that way, now I want to change it. Now I want to write it. So that is the thing that I did in my notes also. Now I want to write it in this way. So now Shubhit's thing is more clearer. See, and whether you do it in put it in that way, you take AE common or whatever you do, you have to finally change all the indices and write it in RABCD form. Because what you are getting from this, what is done in standard, the standard literature, is to call this D, not B. So now you have to change all the indices. So you can call this E also, but then you have to call this as B because you want to write it in the standard form so that you can spell it out clearly. So RABCD. So this is equal to. So what is now being done is the following. You are replacing D by B. This is a lot of change. B by C and C by D. Do this replacement and see what you get. So what we shall get is, this is del, B is C. Good. Now we have got. So now we have got this del C. This is gamma A. C is replaced by D. B is replaced by B. Good. Minus del C is what? C is replaced by D. Gamma A B. D. B is replaced by C. And D is replaced by B. Doesn't matter now because you can shift it because it is symmetric affine connection. So this is what we have got plus gamma A. B is what? B is C. Okay. B is a dummy index. So what we shall do? We shall change it to E. Gamma E. C is E. What is the E now?
E.
Huh? E.
E will be D. E will be D.
My God. So I will remove the earlier thing. So it is really problematic. So it is AD, right? So this one will be D, right?
No, D will be D.
D is B, right? D is B. Very good. So it is better to change this, write it in the AD form or AE form, whatever you like, and keep track of this indices. The last result that I wrote it down here, but I removed that. So this is this, and then you have another term minus gamma. And please take the indices. This will be gamma A. Let me just do it from here. This will be B. E is gamma E. And then what else? E is there. You can write it CB or BC, it doesn't matter. So now, what I was going to tell you is that you don't need to remember this expression. In fact, if you want, you can always look at books to find out what the expression is. But what I was mentioning is that there is a nice way of remembering this expression also. It's the difference of two differentials of gamma, and the difference of two products of gamma. The first term you can immediately write, you just put this index C over here, this goes on top, and then you have only remaining two indices. BB you can write it as BB. And the second term, you put B over here, gamma A over should be always on top, this is CB, this is symmetric connection, so this is BC. And then the other product terms are gamma A, put C over here first. When E comes here, E gets contracted, then you have only two indices which is BB. Then again replace this by BB by BB. And then you have gamma A, E goes here, E goes here, E gets contracted, and then you have BC. So this is the expression for the Riemann curvature tensor. So you don't need to remember anything. And the only important thing is that this transforms a tensor. And the reason I've already mentioned it to you. What we shall now do is something very important. The important thing is that we need to study the symmetric properties of this Riemann curvature tensor of this object. So what do you think will be the symmetric properties of this object? Do you have any idea about the symmetric properties of this object? This is the next question. So, it is anti-symmetric in the last two indices, so that you should be able to see immediately. Also, the first two indices, it should be anti-symmetric in, and that you can see immediately from this expression. So immediately from here, and there is one more property that is also there. Absolutely. What from this object, what we can do is we can actually take this index down, put it over here, and then it will be antisymmetric in the first two indices, and these two indices you can already see, right? It is antisymmetric in the last two indices, but this is something. This part, one of the indexes is up, one of the indexes is down. So you have to take it downstairs and then look at the symmetry property. That you have to do. But what we shall do now is something very interesting. You can get hold of all these properties by using the equivalence principle. So we shall once again go back to the equivalence principle. See what happens. So first property is that this is antisymmetric. You can immediately see that this is antisymmetric in the last two indices. Please check it. Please check this property. Is antisymmetric in C. Are there any more properties? And you are guessing that it should also be antisymmetric in the first two indices, but you have to take it down and see what is happening. Huh? Reject is something to do. Good. Good. So then what you should get? What do you expect to get? Zero. Okay, please check it. Please check this condition. This is called the cyclicity property. So what you are saying is that you just make a cyclic combination of this plus B, BC plus another combination, cyclic permutation, and it should come out to be 0. Check it whether you take it to be 0 or not. Something important. And then you should get also the Bianchi relation. There is another identity which is the Bianchi. Please do it. See whether you get that relation or not. you can naively check the antisymmetry property in AB. See, this is upstairs, this is downstairs, right? So you just do one thing, put this here, or you just replace A by B and B by A, and see, check the antisymmetry property first. Because if it is antisymmetric downstairs, it should be antisymmetric upstairs also. Because after all, it is the tensor. It should retain the symmetry property. So try to check it. So what I am saying is that just this. But then you may fall in a problem. You can understand why you got in a problem? Because if you replace A by B, B by A, then you have to do the same thing over here. But then you have to check whether it is antisymmetric in AB or not. That is a problematic thing. If you work with these gammas, is there a way out? How will you check the antisymmetry property? যেটা কোশ্চেনটা হচ্ছে যে সিরিজের অ্যান্টিসিমেট্রিক তো দেখাই যাচ্ছে just replace C by D, D by C. You can check it. Have you checked it? It is antisymmetric. Good. The question is whether it is antisymmetric in AB or not.
Separate gamma in terms of the matrices.
Separate
Gamma ABD like in terms of the
in terms of the metric tensor. So what you can do is, if you want to check whether this AB it is antisymmetric in these two indices, then it will be very difficult if you keep gamma over here, right? Because what will happen? This will become B, this will become A. Now you have to check whether this is antisymmetric in AB. So that will be difficult. So what you need to do is you need to put gamma in terms of G, because gamma has an expression in terms of the metric tensor. And you have to put it over here. So what will happen? You will find there is a G and derivative of G, G derivative of G, and this you can just forget about. This is too complicated. Gamma into gamma into multiply things, so much amount of things, right? So what is the way out? How will you check, or how will you find the other properties? One property, as all of you are saying, that RABCD plus cyclic formulation, that will be equal to 0. Oh, on this one. What is the way out? Any hint or anything? Huh? Way out of finding, you have to obtain, you have to check whether there are symmetry properties or not, other symmetry properties. The question is whether it is really antisymmetric in the first two indices or not.
Next step is whether it is symmetric or antisymmetric in the first and
Forget about that. I'm worried about this too. How will you do it? As you mentioned, that you have to put the gamma in terms of G. And if you do that, then only you can check whether this is symmetric or antisymmetric in AB.
You can take the pieces down.
Absolutely. By putting, say, you can multiply it by G FA. Then it will come down. Then what will happen? G FA will be multiplied by this. Now you can check the antisymmetry property or symmetry, whether it is symmetry or antisymmetry. But how will you do it? To do that, you have to put the gamma in terms of G. Now the problem is that if you put the gamma in terms of G, you can understand the formula. The formula is very big, because this is G, then derivative of G, then again a derivative is acting outside. Same is for this term. And here there will be product of two G's and product of derivatives of G's. Similar for this term. So it's a huge expression when you put all the gammas in terms of G. It's a very big expression for the Riemann curvature tensor in terms of the metric tensor. So how will you go about it?
another way is we swap BA and CD both. If that is symmetric, that means AC will also be understood.
Yeah, whatever you have to do is you have to write the, as you have mentioned correctly, at the first, that you have to write all the gammas in terms of G, in terms of the metric tensor. But what I am saying is that if you put it in terms of the metric tensor, the formula is very, very huge, and then tracking all the, doing the calculations will become very difficult. So what is the, so is there any physical input that can save us from this huge amount of calculation? You can do it in that way. There is no problem in doing it in that way. But if you want to see, none of you are using your hands because you don't want to do the calculation. Because you know that it is already big. And I totally sympathize with you. This is a huge calculation. If you put it in terms of G, you know what will happen. So what is the way out? That is my question. Is the question clear now? কি করে ছোটটা কি করে করব ছোটটা কিভাবে করব that is the point না না রিচিতে যাব না আপনি রিচিতে আসেন ইমাজিন ভাবে সাগর হ্যাঁ they have already written down the answer this will come to our rescue the equivalence principle will come to our rescue but how what does the equivalence principle tell us the equivalence principle tells us that in any curved space time
আচ্ছা টোটাল ন্যাচারাল কারণে গামা
জিজেকে এটা ইনক্লুড করে দিতে পারে
so
ডেরিভেটিভ পার্ট
so first of all at any point in the curved space time you can erect a locally inertial coordinate system right so in that locally inertial coordinate system what do you have the metric the curved metric is basically like flat Minkowski metric so what will happen the derivative of the metric is zero is the first point only at that point and nowhere else is only at that point and next what will happen if the derivative of this is zero then what is going to happen then gamma is also zero at only at that point so gamma is zero means so your equivalence principle saves us you don't need to calculate these terms you go to a locally inertial frame where your calculations will simplify a lot that is what you are doing so this is zero this term is zero and let me tell you a result from differential geometry the basic result of differential geometry states that this locally inertial coordinate system this is sometimes called the geodesic coordinate system or the normal coordinates a basic result of differential geometry states that normal coordinates at a point exist on a manifold with a symmetric affine connection normal coordinates at a point exist on a manifold with a symmetric affine connection. Only if the manifold has a symmetric affine connection, then normal coordinates exist at any point. This is a basic result of differential geometry. What are these normal coordinates? In this normal coordinate system, all covariant derivatives become partial derivatives. The first thing. And all geodesics becomes locally linear functions of the affine parameter. Only at that point. This is a result from differential geometry. That normal coordinates exist at a point on a manifold with a symmetric affine connection. If it exists, which it does from the result of differential geometry, then at that point it basically tells you that all the covariant derivatives becomes partial derivatives. Covariant derivative becoming partial derivatives means what? The gammas are zero. And second thing is that the geodesics are linear functions of the affine parameter.
For that case, every gamma will be zero. So the transition is always zero.
The previous class I I showed the equivalence of, you missed that class. I proved the equivalence of equivalence principle with metric compatibility. You asked the question previously. We did it. And here, what I'm saying is that the gammas are zero in normal coordinates. So this result of differential geometry that was there already, this was actually implemented by Einstein. He said that instead of normal coordinates, we have a local inertial frame. In a curved spacetime, which describes gravity, at every point on that curved spacetime, you have a local inertial frame. What you are saying is that gamma is zero, so everything is zero. That is not true. Why? Because gamma is zero, but it does not mean that the derivative of gamma is also zero. Okay. Basically, gamma at that point zero, but gamma is only zero at that point. So you can do it in an alternative way. What you can do is to go back to this Newtonian limit that I discussed in the previous lecture. You can replace G by eta plus H and do the calculation by incorporating that and neglecting all terms of the order of H square. Neglect all terms of the order of H square. Then also, whatever we get from this analysis, we will get the same results by using that form also. It basically tells you that only at that point the metric can be replaced by eta AB, and these are the fluctuations around that point, HA, which are small. So at that point, P, the derivative of the metric is zero because it is eta AB. So del C GAB is equal to 0 at that point P, and also gamma at the point P is equal to 0. That local inertial frame. So with this, so what we have done is we have used the equivalence principle now to do the calculation or simplify our calculations. So these two terms are gone. You have only these two terms. So in these two terms, you can now forget about this. So this is gone. So this is equal to del C replace gamma ABD by the formula that you have. The formula is half G del E G CD plus del E. This is the first term. So please note that in that thing we have already implemented this condition. We need to implement this condition. We have not done that yet. Minus, again replace this by the metric tensor of G is E del P G C plus del C G B E minus del E G C. This is what we have. Right? The product of gammas we don't need to write because this is zero. That local inertial frame. Now we have to impose, we want to impose this condition. And this condition is very simple to impose. From here, you will have two terms. Del C will act on this term, del C will act on this term. But del C acting on this term is what? Is zero. Because del C acting on this term is del C GAE times again del D this. All these terms are zero. So you don't need to act this here. So what you have is half. Let's replace this by LC, LC, LC. Similarly, this will be LD. Our this will be LD, LD, LD. What we have done is you will get two terms. LC acting on this, that is what? Look at the board.
Why is this UI?
Because locally, what is the metric? G is what?
These which are
So what is the derivative of eta?
we are not we are saying that eta to be I mean the gamma to be 0 I mean at point, but
If the derivative of G is 0, then gamma is 0.
yeah,
Would that understand?
yeah, but we are not applying everywhere that gamma is 0.
So we are applying everywhere gamma is 0. We are not saying
Second derivative there it is not.
first derivative of gamma is not 0. And this term is the second derivative of G.
That is not.
That is not 0. The first derivative of G is 0. That implies gamma is 0. But the second derivative of G is not 0. That implies the second derivative of gamma is also not 0. So everything is consistent. So we have these two terms. Now I leave it on to you. Please find out what is there a cancellation or I think there should be some cancellation. These two terms should cancel. They are cancelling, right? This is D, right? So let me write down the expression, final expression. So what we have, let me write down the conditions also. L, C, G, B only at that point. We are now doing the calculation only at that point, right? We are doing local calculations. We are saying that LCGAB at that point is 0. If this is 0, then gamma, this implies that gamma at the point B must be 0. But what we are saying is that del E del C GAB is not equal to 0. Therefore, the derivative of the derivative of gamma is also not equal to 0. Okay. So what we have got is from this expression is half D A E del C del E first term minus del G del E GBC. The second term, I have written these two terms, this and this term. And then we shall have plus, let me write down the other terms. Plus del G del E GBC, this is this term, minus this term. Actually, let me write it down then. Let me check.
There is a mistake of plus minus.
Okay, there can be a mistake. So you please write the correct result in your notebooks. This is plus. I have removed the first. This is LCD GED. Correct. This term is correct.
Yes.
Very good. This term is correct. Okay. Minus minus del P GBC. This term is also correct. It is okay. If I make any mistake, please correct it in your notebooks. That is what is important. I just check it with my own result. Half GAE del C del E GED. Fine, that is correct. minus del C del E GBE, that is also correct. Minus plus del D del E GBC, this is correct. Del D del E GCE, this is also correct. Seems to be correct, what I have got. But although I did not write this line in my notebook, that line is not there. So this I write down here. Okay. So now you can see that it is very simple to see all the symmetry properties. One more step that we shall do is we shall multiply. I want to take this index down, so I will just I multiplied it. What index did I use? I used F. F. So this will become GAF. So this is GAF, but that is equal to delta GF. Right? So whatever, so what, replace all the E's by F's. So let us do that and remove this one. Replace all E's by F's. You have got this nice result. This is R F B C D. Is it okay? Very good. So now we have a very nice expression which you can actually tackle. It's not that big. And you can remove all these intermediate steps. So, and now what I would like to do is I would like to write it in a nice way. I will just replace F by A. This is my final change. A, A, A. So this is R. This is my final expression. Please check whether this is correct or not. Up del C del B GAD minus del D del B GAC is also fine. Minus del C del A GBD plus del D del A GBC. So this is my final expression for RABC. And now please check whether it is antisymmetric in CV. You have already checked it, but you can check it once more. And also check whether it is antisymmetric in AB or not. Please do the calculation quickly. It's a very quick calculation. It will not take much time. Is antisymmetric in AB? So previously you see that to check the antisymmetry in the first two indices, you had to, it was actually in a mixed tensor form, and you had to do a lot of calculations. But all your calculations have simplified this analysis, and you can immediately see the antisymmetry in the first two indices. And the important thing is that if it is antisymmetric in the first two indices, you can also do this. You can put this up. See what happens. So if you put this up, this will be going up. This is going up. What is GAD? Delta AD. So this term is 0. Okay? Check it whether it is antisymmetric. Yes. You can also do that. Okay? But now, what we shall do is we shall first take this combination. What do I mean by this notation? What I mean is R A B E plus R A B C plus R A C D E. Okay. Please calculate this immediately. If you calculate this will come out to be 0. Right? And in that calculation, you can understand that earlier you had to do so much amount of calculation. But you just use this expression, this simplified expression. To do this calculation, it will come out to be 0. Now the question is, how many number of independent components are there for this object? Do one more calculation. Please check. See, this AB, I can call it to be capital A, this to be capital A. Okay. And what I can do is, I can just calculate this thing, which is RCD AB. RCD AB. So if you RCD AB, so I'm just exchanging the blocks, and if you do that exchange, you will see that this is equal to this. It's symmetric under block exchange. So now the question is, how many independent components are there for this RABC? Without knowing any symmetry property, how many independent components should be there? Huh? So what, that is 256. So there should be 256 independent components. But it turns out that this is antisymmetric in this is antisymmetric in this. So just consider this matrix RAB. So what kind of a matrix should it be? It should be a 6 by 6 matrix. Right? Because AB, this sector is antisymmetric in AB. So number of independent components is what? 4, 4 is antisymmetric in AB. So number of independent components is 6. So this is also 6. So RAB, capital A, capital B, this is a 6 by 6 matrix, and that is symmetric. So how many independent components? 6 into 7 by 2. So that is 21 components. Right? So let me, this is 6 because of antisymmetry, 6 independent components. This is also 6. Symmetric in AB. So this is 6 into 7 by 2. So 21 independent components. But you have one condition, constraint condition, cyclicity. This is the cyclicity condition. So that reduces 1. So you have 20 independent components. So this object has 20 independent components. What were the number of independent components of the metric tensor? 10. So GAB, the number of, it was symmetric object. So number of independent components is 4 into 5 by 2, that is 10. The Riemann tensor, Riemann curvature tensor has 20 independent components. Okay, so this part is done. So do you have any questions at this point? Because we need to do another calculation with this object. Please, questions. This one should. You have any doubts, questions? Yes.
So, during the exam discussion and the zebra for that symmetry, there will be three components. I mean, why is six?
Because this has 4 components, this is 4. So it's a 4 by 4 matrix, anti-symmetry. So 3 plus 2 plus 1. Diagonal is or 0.
The two blocks are symmetric, that's why you are doing 6 into 7 by 2.
This R capital AB is a 6 by 6 matrix, which is symmetric. So the number of independent components will be 6, and then you go on. So it will be 6 into 7 by 2. 6 plus 5 plus 4 plus 3 plus 2 plus 1. So 1 plus 2, 6. 6 into 7 by 2. So in 21 components, one cyclicity condition. So that reduces 1. Therefore, we have 20 independent components. Now, what we shall calculate next is the following thing. That is also very important. We need to calculate an object of this form. And that is, by this, what we mean is the following. This is this R plus this is what we shall calculate. So this is by definition. This is once again it is cyclic permutation of these three indices. By definition, it is equal to this. So we want to calculate the covariant derivative of this Riemann curvature tensor. So you can see that it is a quantavariant tensor now, and it has 4 indices. Then you are taking covariant derivative of that. So it will be a huge expression. Once again, it is a huge expression. But what we shall do is, we shall use this expression instead of that. We shall do all calculations locally. And if you do all calculations locally, then what will happen?
It will be partial.
So the first thing is that the result of differential geometry or the equivalence principle tells you that this will be very all covariant derivatives will be replaced by partial derivatives. That simplifies the calculation a lot. What you need to calculate is you need to calculate this and use this expression while you calculate this. So let us calculate this. Del E R A B C D, nothing but del E, del E. So that is the first thing. Now we need to calculate del E R E A C. That will be what? Very easy to write it down. C. This is del E. So E gets replaced by B. This will be del B. C. C is C. Don't replace C. This is del C. B. B gets replaced by A. A gets replaced by E. D remains the same. E gets replaced by B. Do the same thing. Here C remains the same. Don't replace C. B is here. B gets replaced by A, so you replace this by A. Once again, A gets replaced by E, so this becomes GE. E remains. Now the other terms minus del. Once again is B. D. D is what? D is A. A is what? A is E. So this is the second term plus del E is B. D del A is A. C minus is B. C del A is B. B is it okay? Was that 11? So from here, and you need to write down one more term. Other term is del A R E E E. So what I am doing is I'm replacing. You can do it from this one also. You can do it from this one also. Whatever you like. You replace B is replaced by A. Del A. Del C. E. B is replaced by B. Done. Del B. B is A. And there should be another term. 1, 2, 3, 4. 1, 2, 3, 4.
There are two ways.
Two shapes. Yeah, right, correct. Just let E. Then what are then E. Sure. I'm not checking. Very good. So this A. A is E. Very good. So B is what? B is A. Del B. B will give me B. এটা বলো কি হবে? E. And then this G is C. BC. And the last two terms, please tell me. Del তোমরা করছো না ক্যালকুলেশন করছো নাকি আমি করব আচ্ছা করো তাহলে করে আমাকে বলো কি হবে del D তারপরে del B G B কি করে হবে EC okay and the last term del A del C del G right now we just add it up and see what happens 0 হচ্ছে so if you add it up then you get this to be equal to 0 and this is an identity these are called Bianchi identities so you have similar identities in electrodynamics also they're called Bianchi identity or identities because for you can put whatever component you like and you get many such identities. So these are Bianchi identities.
Symmetric addition of the code, cyclic addition of the covalent derivative equals to 0, that is the Bianchi.
Yes, that is what I am saying. This is 0. This is 0. Symmetric. The addition of covalent derivative of this is 0. The Bianchi identity. And it is not only this thing, you could have done it for the other two indices also, right indices. That is also symmetric addition of the covariant derivatives of. So you just keep this to fixed and just do it as
Symmetry. So you
do that. So it is also zero. And that is what?
that is symmetry, like AB and C.
There, so you can always do that. So there, that is also equal to 0, and that is the Bianchi identity. So this is a very important identity that you have here, and we shall now progress with this Bianchi identity. Let us write this Bianchi identity in a nice form. Shall start from here. See what happens. কি বলো নিশ্চয়ই আছে নিশ্চয়ই আছে but why do you want to go there now big group connection তো আছেই yes আছেই এখানে huge group structure আছে because general relativity has diffeomorphism invariance so diffeomorphism is the group symmetry group here in this case huh diffeomorphism. So there is a connection. Not only that, this Bianchi identity has the fact that it is a connection with Lie groups can be easily seen because we have the Jacobi identity. If you write down the symmetric grad commutator, grad A, comma grad B, comma grad C commutator plus cyclic combination that is equal that should be equal to 0. That is the Jacobi identity of the covariant derivatives. That is the Jacobi identity. Now these covariant derivatives, they have connection with Lie groups, and that Jacobi identity has connection with this Bianchi identity. So there must be some connection, but we are not looking at that now. We are looking into the what we shall do is our aim is to understand general theory of relativity. First, obviously when you want to study general theory of relativity, you need some mathematical structure. So you need to have some exposure to this Riemann curvature and all these things. You need to know what these things are. But then our aim is to go and look for physical phenomena. What do you get out of it? There is a connection. There must be there is a deep mathematical connection. You can understand already. You can understand that there must be some very deep mathematical connection because the equivalence principle is the same as using normal coordinates in differential geometry. There is a deep mathematical connection, no doubt about it. But we shall not. The aim of what we are doing now, the aim of this course is not to look at those deep mathematical connections, rather to have an understanding of what general theory of relativity is and what do you get out of it. What is the physical phenomena that you can explain or that you can predict from this theory. That is our aim. But if you want to study a more mathematical version, or if you are interested in mathematical connections of general theory of relativity with differential geometry, then that should be a different course altogether. That should be a more advanced course. Okay, so what we shall now try to do is, you can see that this combination is equal to 0. So let me just write down this equation once more. This is this plus that B R E A plus Z A R E. So we have this thing, and now what we shall do is we shall multiply this by this. See what happens. So what do you think this will simplify to? So, huh? How? Simplify to the so then this come to the board and try to derive it. করে?
Contract for human tensor with GAC that will give the reduction inside.
But how can you contract it? GAC is the offset. You're right.
Covariant derivative of the metric is zero.
Tell me please.
Covariant derivative of the metric is zero.
So what we can write now is just multiply, put this inside. So this is basically that B, C, R, E, A, C, E plus grad A, C, R, C. So this we can do because of metric compatibility, as you are saying. You can put this inside covariant derivative of the metric tensor is 0. So you can do that. Now you can see that this object, when you contract it with the metric tensor, then you can write it like this. That goes up, and there is another tensor. Now you see the first and the third. If you contract, you get what is known as the VD tensor. VD. This is the VD tensor. So this VD tensor you get it out of the Riemann tensor by contracting the first and third elements. And you can also write down an expression of the leaky tensor in terms of the gammas. Because you just contract the appropriate index in that expression, and you will get the expression for the leaky tensor. Good. Here, what you can do is the following.
Antisymmetry property use for
Antisymmetry use for antisymmetry use for here. R A G A C R Okay, I am doing it. Sorry. So fine, it's not problematic. In my notes, it is given done in a different way. So I use the antisymmetry of this and this. So that is why it is done in a different way. Now I have to figure it out. So can you figure it out? What will I do in the second term?
minus of R BD.
Minus of
R BD. Sorry, R BD. BD. Minus of R BD.
RB. RB.
R minus of R E. Minus of R E.
You also post it.
Minus R E.
REB.
পুরোটা হবে minus R E.
আমি এক্সচেঞ্জ করে দেব। So you want me to change it, right?
It will be R A E C D. A B.
So let me use the property first. This will be what? AB.
A B power.
Is this correct? So this is this term. And what about the last term? What can we do with that one? We need to do something with that one. GAC. So
We can apply the symmetry property.
CD, DE, and then can write this. Is it okay? This is fine. This is correct. And this is also your check, right? This is correct. Now try to simplify with this. See what, as George mentioned, that you should end up with the.
You have to see contract with another.
Get a contract. I contract it. Simplify it. That is what I am saying. Please simplify it. So this is, so that is assuming this part RBD, the repeat tensor, and you contract it with GBD. So if you contract it with GBD multiplied by GBD, GBD contracted. Once again, you can put it inside because of metric compatibility. This is GBD plus GBD. GBD RBD, this object, nothing but RBD, which is the leaky scalar. The leaky scalar. So you get this. Leaky, the property of this leaky tensor is that it is symmetric in the two indices. You can check it. RAB is symmetric in the two indices, leaky tensor. So you can write this as RBC. Okay. And now GBD is there. You can raise this index and write this as B. Drop this. That's fine. And what about this one?
First we use the anti-symmetric property
Huh?
in the first two indices, and then
So I can use this. Let's say this. And then what can we do?
then D will go up upstairs, then again RA will come.
Okay. So DD. So this is D. This is gone. BA. First and third index contracted. So this is nothing but RAE. Is it okay? This is RAE. This is correct. So use all these. So the trick is that you have to use the symmetry properties, symmetry and anti-symmetry properties of the demand tensor as well as the leaky tensor. This is nothing but R. Minus that E. Remove this part. That is also the same term. So this is twice, right? Equal to 0. So ultimately, the Bianchi identity with contractions simplify to this form. I made some mistake, right? Okay. So this is fine, and therefore you can write this as grad A R A E. So let me now replace this by B. E minus or equal to is it okay? So this term I can now write it down as grad A R delta. Are you having problems? IPSD. কোথায় প্রবলেম বলো তাহলে I will go a little bit slow. হ্যাঁ তোমাকে বোর্ডে গিয়ে লেখো নাহলে ওইখানে ওই জিনিসটা লেখো then we can do it. Yeah. Which cycle? And is equal to 0. না ওটা গ্র্যাড ই ওটা আর বিডি ছিল না ওটা আর
এ শুধু আর এ
এখানে কোনো বি হবে না
বি এ
আর এখানেও কিছু হবে না এটাও আর হয়ে গেছে because this is basically the chapter এটা হচ্ছে এই অবজেক্টটা হচ্ছে জিবিডি আর বিডি but we can write this down as RBD which is nothing but this ঠিক আছে তাহলে ফার্স্ট টার্মটা কি আর সেকেন্ড টার্মে গ্র্যাড বি যেটা তুমি লিখেছো this term you have written it correctly এই টার্মটা যা লিখেছো এখানে যদি ইনডেক্স পাও তাহলে তুমি বুঝবে ভুল আছে নিজেই বার করতে পারবে কারণ কটা ইনডেক্স আছে এটা ডামি ইনডেক্স আছে তাহলে একটাই ফ্রি ইনডেক্স এটাও ডামি ইনডেক্স দুটো ফ্রি ইনডেক্স থাকতে পারে so there must be some errors then you can appropriately correct okay so ultimately after all these calculations what we have ended up with is the following equation or following not I should not say equation rather a following identity this is the identity that we so grad u r minus twice this now this if you simplify you will get it to be equal to this this term I'm writing it like this please check whether you can do it so you can write it like this therefore this is once again metric compatible so what you can write is you can write half grad a delta a b right therefore what you get is grad a r a b minus half delta a b to 0 so this is the final equation that you get here and you can write this you can call this something G capital G A B therefore the final equation is or final identity is where GAB and from here you can immediately lower down the indices you can write GA all the indices are down now this is basically AB minus half when you lower this index down this Kronecker delta will become metric tensor once again and this tensor is called known as the Einstein tensor this is the Einstein tensor and what it says this is another form this is once again the binary identity because we have derived it this form we have got it from the binary identity and in getting to this binary identity we have introduced two new quantities one is the Ricci tensor which is RAB which is nothing but RCAB the Ricci tensor that you get by contracting the first and the third indices of the Riemann tensor and the Ricci scalar which is we contract both the indices of the Ricci tensor and you get the Ricci scalar. So in getting to this form of the binary, this is another form of the binary identity we have introduced the Ricci tensor and the Ricci scalar. Ricci tensor is symmetric in AB. You can check it because you have an expression of the Riemann tensor in terms of the gammas. Therefore, you have an expression of the Ricci tensor also in terms of the gammas. You just need to contract the indices, and you can check that it is symmetric in AB. And then you have the final quantity, which is called the curvature scalar, because it does not have any index. Therefore, it transforms in as like a scalar, it is an ordinary function. And if you introduce these two quantities, then you can see that this particular combination, this particular tensor, that is called as the Einstein tensor, that is covariantly conserved. Okay. So this is once again, this is the Bianchi identity, and this is not an equation of motion. It's an identity. You know the difference between an identity and an equation of motion. Okay. Now the important thing is that what you know from your standard physics is that the energy momentum tensor of the stress energy tensor is also some quantity that must be covariantly conserved. Okay. The stress energy tensor, which comes from which gives you the matter sector of your universe, that also should be covariantly conserved. And from here, you can actually, since we have gone through all these calculations and obtained these results, you can say that okay.
So are we using an answers?
No, where your stress energy tensor should be covariantly conserved. Because energy should be conserved, momentum should be conserved. So it must be covariantly conserved, because otherwise the conservation in a curved space-time, in a curved space-time, you have to get covariant transformation laws. All the partial derivatives should be replaced by covariant derivatives.
So when you move that energy conserving flat space, even in the Indian, but we are generalizing it to the.
You will get it to the same. See, energy momentum conservation is something sacred. You don't want to. There should be no magic that if you go from flat space-time to curved space-time, it will be violated. Then there will be a problem. You want it to hold everywhere, not in flat space-time or curved space-time. That is something sacred principle that we all obey. That energy should be conserved and momentum should be conserved, angular momentum should be conserved. These are principles. There should be physical principles. Otherwise, there is a problem. You know the famous story of beta decay, right? Nuclear beta decay story you have heard. You know what was the problem there? They studied nuclear physics. Huh? You know, remember what nuclear beta decay is? What? What happens when a neutron decays? What happens when a neutron decays? Goes to a very good proton and electron. Okay. So let us go to some. Okay. So what was found experimentally is that you get a continuous spectrum. This electron has a continuous spectrum of energies. How can that be? So at the time when this was discovered first, you have a continuous spectrum of energy of the electron, right? So people thought that, so how can you have this continuous spectrum of energy for the electron? Because this has a fixed energy, this has a fixed energy. So how can you have a spectrum of energy for the electron? If energy conservation is sacred, then this must have a fixed energy, right? So, but there was no answer to this question, to this dilemma. So people even went to the extent by saying that maybe God violates the conservation of energy principle in case of nuclear fusion. So when people were desperate to say that okay, maybe here we have an example where energy conservation principle is actually violated. And this was actually when people were so desperate, so they wanted to say that okay, maybe we have to get rid of this. But ultimately, it was realized no, there is nothing, there is no problem because an anti-neutrino is also coming out from this nuclear beta decay, and that also has a continuous spectrum. For each energy electron, anti-neutrino has another. So energy conservation principle. So in fact, anti-neutrino was predicted first because it is very, it is very difficult to detect neutrinos because neutrinos are very, very weakly interacting particles. Several millions of neutrinos are passing through our bodies and nothing is happening to us. It's radiation, right? It's radiation, but nothing is happening to us. Why? Because it is not ionizing anything. It is going through our body and fast going to the earth. It's very, very weakly interacting. Strong যদি ভালো ইন্টারঅ্যাকশন করতো তাহলে আমাদের রেডিয়েশনের ক্ষতি হয়ে যেত ইটস রেডিয়েশন পাসিং থ্রু আওয়ার বডি নিউট্রিনোস আর রেডিয়েশন not photons it has some mass but it is obviously these are cosmic particles they are coming from the there are solar neutrinos can come also from the space and whatever it is coming out from the sun and is passing through our bodies but only thing is the good thing is that they are very weakly interacting, nothing is happening. The fact that they are weakly interacting makes their detection even more difficult. You cannot detect neutrinos very easily. So it was actually proposed that there must be some hidden particle there which is coming out, so that not only in the neutron, in the beta decay, you see neutron has spin half, proton has spin half, electron has spin half. So angular momentum conservation is also not there. So third particle neutrino was introduced, anti-neutrino. At that time it is anti-neutrino or neutrino. So it was introduced and you can conserve the angular momentum as well as you can explain why do you get a broad spectrum of energy of the electron. Because now it is a three body problem because three particles are coming out. So there is no problem with energy conservation, right? So you don't want to spoil your energy conservation principle. Whatever is happening in flat space-time, energy conservation was there, and we have learned that energy conservation must be there from our school days. So it must be there in curved space-time also. So energy momentum tensor is something which is covalently conserved. Now that gives you maybe a clue or maybe tell us something that okay, we have got from the geometry side, we have got some tensor which is covalently conserved. From the matter side, we have got some tensor. We know that the energy momentum tensor must be covalently conserved. And so let's do one thing. Let's equate the two. Because both are covalently. And this is, I will give you a sort of derivation, a heuristic derivation of this. And this particular result known as the famous Einstein field equations of GRC. So on one side you have pure geometry, on one side you have the matter sector, this is the stress energy tensor, and what Einstein did was equate the two. From here, per se, okay, this is covalently conserved. You know of one such tensor from the matter side, this is also covalently conserved. That does not tell us, that does not indicate, or that does not tell us that we should equate the two. But Einstein actually equated it, and in the next lecture we shall try to give a heuristic derivation of this equation. But for that, we need one more equation, and that we shall derive in the next class. And that equation is, do you have any hint of what that equation is? Huh? Houses, what houses?
For
That equation is very good. Obviously, we need the Newtonian limit equation. In fact, we studied the Newtonian limit in the previous lecture. We need the Newtonian limit equation, but one more equation we shall need, and then we will be able to give a heuristic derivation of this equation. And that equation is known as the geodesic deviation equation. We have learned the geodesic equation. Now we will study the geodesic deviation equation. What does that say? It tells you that you have two geodesics. You have many geodesics. You have said congruence of geodesics, and now we want to find an equation for the deviation between two geodesics. So, are they always moving parallel to each other, or are they coming closer? Are they going out? So, if they are not parallel always, then it tells you that the deviation vector of two geodesics is actually changing with time. So that equation is known as the geodesic deviation equation. And once we get hold of the geodesic deviation equation, then you can really start and try to get to this equation in a heuristic. Obviously, we need Newton's equation. As we say, Newton's equation will be required. You need to make an intelligent jump also. With that extra jump, Newtonian limit, and the geodesic deviation equation, you will be able to get this equation. And then, suppose I get to this equation. Your equation should be consistent, right? The equation should be consistent. And once you get to this equation, you are sure that this is the correct equation. Why? Because the left hand side is covariantly conserved, that we have proved now by Bianchi identity. The right hand side is also covariantly conserved. So your equation is consistent. What Einstein wrote historically, what he wrote down was RAB is equal to some factor here. In one of his papers, he wrote down this equation. And then he realized that this equation is not correct because this left hand side is not covariantly conserved. He's always assuming in his head that this side is always covariantly conserved. So this side must be covariantly conserved. Therefore, this equation cannot be right. So in his next paper, final paper, he said that okay, the previous equation is not correct, and this is the final equation. Better.
So idea of energy moment and tensor being properly conserved comes from the energy moment and tensor is whether current.
I'll do it from there.
Okay.
I'll do it from there. But you have to come to the class.
Otherwise,
we will miss it.
Sir, actually, there was a mistake. I made mistake in dates. I mean,
You remember that
I বৃহস্পতিবার ক্লাসে এসে বসেছিলাম যে ক্লাস হচ্ছে না মানে আমরা বৃহস্পতিবার থেকে বুধবার ভাবছি
So you have a time like killing vector now. Okay, so let us stop here for today, and in the next class we shall start with geodesic deviation equation, and then